Swayam Prabha. Digital India. Educated India.
Good morning. Good. Okay. We had some foundations of sort of computing and CPU in the morning session. Now I will build upon that. So this is going to be the agenda that will start with what is HPC. Then how do you build a HPC system? All of us know how a desktop is or a server is. We will go beyond that and see how HPC works. Then we know that it's a parallel computer. So how do you adapt your programs to this parallelization? And what are the paradigms that are generally used for parallelizing your code? And I will briefly touch upon what are the grand challenge problems where HPC is very frequently used. Okay, so we will, since I have a challenge that some of you are like undergraduate students, some of you are PhD students, so your knowledge about HPC may be varying. So I will start with the basics for those who do not know what HPC is, so that others who know about it, maybe it will be a refresh for them. So the principle on which HPC or parallel programming works is that you have a large problem to solve. And a large problem can be solved on any computing system. But sometimes you face a problem that it takes time, and you can't afford to give as much time. A classic example could be, let's say you have a weather forecasting code, any computer, even desktop can run it, because after all it's a code, it can run it. And you want to predict tomorrow's weather. And suppose you get that you start it now, and suppose you get the result which is accurate, but you get it tomorrow evening. That's of no use. You want it today evening, so that you can tell that, okay, the weather is going to be like this tomorrow, and if there is anything to be taken care of, then you can take care well in time. So what is the solution? Like you look at this problem, and can it be divided into smaller problems, and you have more number of compute elements, and can you run on them concurrently? If that can be done, then we are doing what is called as parallel computing. So that is a basic way in which we try to use parallel computing to solve a large problem, but we need to see whether that problem can be broken down. So I've written often. It doesn't mean always any problem can be broken down. Some problems are inherently serial, which cannot make use of parallel computing, but a large set of problems are of this nature. So that is the principle on which parallel processing works. So you have now first step is you have broken down into multiple smaller problems. Then you assign multiple processing elements. So you need multiple processing elements to which this smaller task can be, or the concurrent task can be assigned. There is another way of looking at it, what is called as, the word that you will always hear is what is called as distributed computing. Okay? So that is very close to, it's inherently a parallel computing kind of thing, but the key lies here in the fact that it is solving a task typically which are isolated and heterogeneous in nature. That is what slightly makes it different, in the sense that now you can assume that suppose you have 10 desktop computers. Okay? These are isolated, they are autonomous in nature, but if you can make an Ethernet or some network whom you can use it to connect them, then you have what is called as a distributed computing. So at higher level, maybe a homogeneous system with lot of processing element inside one system, or a distributed system like this, they will serve your purpose, but the programming model required may be slightly different, which we shall see in the subsequent slides. So now we come to HPC. So the basic thing, in the morning we saw how you can run a serial program faster, what are the things that you can do, like pipelining, etc. Now when you want to go beyond this, have parallel computing, then the next step is what is called as high performance computing. So how do we define high performance computing? One of the definition is here, which says that you use a set of computing technologies which are required, which inherently show characteristics where fast numeric simulation, modeling, data processing, all these things are required. So when you have a situation like this, then you use high performance computing. And another attribute where HPC is used is that requires lot of mathematical calculations. And in the morning, as Professor Mayank said, that typically these calculations are floating point. Because you have to have accurate results, you are doing some kind of modeling of some situation, like weather is modeled, then you simulate that, you take the initial conditions, you simulate that, and you reach the conditions that would be tomorrow. So that is what we do in HPC. And the another way of looking at it is, which I already mentioned some time ago, is that the compute power that you have, you unleash it to execute certain applications extremely fast, right? So as a result, what you can do is, as I said, weather is one example which is time bound, or let's say you are doing a crash simulation of a car, then you change some parameter, then again simulate. So what you are able to do is you are do more iterations in a given time. That's another reason why this extremely fast nature of computing helps us in doing more things in a given time. Either task is predefined, that can be made faster, or you have to do too many iterations in a given time, you can do more iterations because each task is finishing extremely faster. Okay. So there are also definitions for HPC. You can form your own. These are the two which I thought would make sense. So it inherently uses parallel processing. We all acknowledge that. We can do that, run those advanced applications efficiently, means you dedicate the hardware solely for running that application. Unlike in the morning, as we said, if you have a task switching, then there are overheads. So if you look on time scale, a task is running, there is a switching time, next task is running. So the switching time eats up the actual time that is required for running your task. So if you don't have that, just one application, continuously run it, you can do it efficiently. Reliability comes from the hardware that is built in inside that, which is very high speed and reliable. And then as a result, you get the results quickly. Now, other definition which is very important, why we call it a certain computer as a supercomputer is because it is a system that performs at the currently highest operational rate for computers. Now, to give a very simple example, the first Param system that CDAC built in the year 1991 had a capacity of 1 gigaflops. Okay, so 1 into 10 raised to 6 floating point operations in a second. I think you would be surprised if I tell you that the mobile that you are carrying in your pocket is faster than that today. But you have gone forward in 30 years. So, of course, so what compute power was supercomputer at in year X will no longer remain a supercomputer, let's say 3 years down the line or 4 years down the line. Something better would come up. Okay? So it's a shifting target. As of today, as I mentioned yesterday, about 166 petaflop is a state of art. And in the top 500, so don't write that number, maybe we can check what is the top 500. So there are two metrics to that. One is the theoretical peak power, which can be calculated by multiplied the frequencies, cycles per instructions, how many cores, and you get a theoretical. Then you run a code called as linpack, and that linpack gives you a result. That result is used for computing. So I will maybe in the next talk I will tell you about that top 500. But point I am trying to make is there is some number which is more than 150 petaflop, which is the maximum compute power that we have today in a single site. So this is important that this is a shifting target. And HPC, Wikipedia says that it uses supercomputer and clusters. I will introduce this subsequently to solve advanced computing problems. That's like telling it in a plain English. Okay. So these slides will be shared, so you need not write what is seen here, but you may write something that you find interesting or which I say, but it's not written here. Moving ahead, we will go to the basics. Many of you would have studied this Flynn's taxonomy if you are a computer science student. So this was in 1966 that this scientist, he proposed how computers can be classified. So as was mentioned in the morning, we have something called as an instruction. That instruction works on data. So in a simplest form, you have a single instruction that is operating on all the processors. So we call it as single instruction. If there are multiple instructions which are operating, then we will say multiple instructions. So you have different processors, they may be executing different instructions. So that is one way of having attribute for the instruction. Same attribute can be applied to data, wherein the data is single, in which case all processors are operating on the same data, or there are multiple data, which means the different processors are operating on different data. So with this we have 4 combinations, okay, which is single instruction, multiple data, or multiple instructions, single data. So here you see that there is only one data path and there is only one processor. So single data stream operating, which is operated upon by a single stream of instructions, or the data is same but there are multiple processing units. I will explain each one of them in the subsequent slide. Then other important thing is that you have the same instruction, single instruction, but each instruction is taking different set of data from the different pool, or the last one is the instructions are different, the data is also different. So you have multiple instruction, multiple data. So let me explain this, each one of these, what is shown here diagrammatically. So SISD, single instruction, single data, which means one processing unit is fetching a data at a time and operating on it. This is a classical single CPU. Like if you have an 8085 based system, you must have all know about this processor, 8085, simplest of the process first that Intel made, then came x86. So if you have a single x86 system and one program running on it, not even Windows, simple MS-DOS kind of thing, that the first operating system that Bill Gates built, if you have a system like this, it will be of this class. So no parallelism, but this is the building block. Single, it's a serial computer, serial program. Then comes single instruction but multiple data, which means that you have a computer which operates on multiple data stream. So I mean a good example of this is, let's assume you are processing the graphics on the screen. Let's say there are some 1000 pixels by 1000 pixels on the screen. You can tile it. Suppose you have 2 processors, you can tile it, divide it into 500 by 1000 and 500 by 1000. If you have 4 CPUs, you can make it 500 by 500, 500 by 500, right? So if each, what you wish to do, suppose you blank the entire screen, which means you want to make all the pixels 0, then you can operate, one processor can operate on 1/4 of the tile. What are we doing here? We are doing, the instruction is same. What is it? Make it 0, but data is multiple. So parallelly you are working on 4 sets of data. So that is a typical thing called as SIMD. This is being used now, I will tell more about it later. So this is called as vector computers, like Cray, the first Cray that was made, it used this vector processing. And this vector processing helps in certain kinds of programs, okay. This is an important class of computers which is called as SIMD, okay. So these SISD, I mean that is what the classical computer is, SIMD is vector processing. Then comes multiple instruction operating on a single data. So now this architecture is rarely implemented, because if multiple instructions are operating on the same data, they are going to produce the same result. So there is not much fun in it, but they are used for fault tolerance. Means there are some systems that take crucial decisions, like a nuclear control reactor, or in a railway yard, you want to take how the signals will be generated. So if you want fault tolerance, meaning 2 computers working on the same data, and if their results are matching, you say that the result is correct, okay. So where you need redundancy, where you need fault tolerance, such systems are used, but not commonly. MIMD, yes, they are used because they are distributed processing that I told you, each unit has got its own data. So most of the parallel computers are of this type, that each one of them is operating on its data. They may also incorporate what is called as SIMD, as the example that I gave you, okay. So moving ahead, how were computers built earlier and how they are built now? So an example is that suppose this is an earth mover. It's a big earth mover and it can move, let's say, some 1,000 square feet of earth in a given time. Okay, suppose 1,000 cubic meter or whatever is not good enough for you. You want it to be double. What will you do if the machine is of this type? You will build another machine which will have bigger capacity, which means the entire design will have to change. You will have to need more powerful engines. You will need bigger spatulas. All this will change. Okay, so that is how computers were built in 80s and 90s. The Cray supercomputer is an example of that. You want higher power, more power, build another bigger computer. But today, what we are doing is like this. So now same example. Suppose you have to move 1,000 square meters. Okay, you have 10 such units. Okay, each one has a capacity of only 100, but you deploy 10 of them. Suppose you want to double the capacity, what will you do in this case? Put how many? 20 of them, right? So deploying 20 of them becomes much easier. You have to just buy them and put it. That's what we do. Build commodity off-the-shelf components. So you have a server class machine. If you take 10 of them, you will get some compute power. You connect 20 of them, you will get theoretically double the compute power. You put 10 times that, you will get 10 times the compute power. So this is the technology that is used today, which says you use what is called as cluster computing. That is multiple instruction, multiple data or a cluster. But then you need a high-speed network to connect these compute elements. So that is what is shown here. This is a Cray supercomputer, custom made for a given compute power. You want more power, build another computer like this. So this is Param UR2 at CDAC Pune, half a petaflop system built using 288 nodes. If we had used 500 nodes, instead of half petaflop, it would have become 1 petaflop. Because now you can't see it here, but each rack has got 9 nodes. And so many nodes makes it 288 nodes, each having 32 processor, 32 cores, etc., etc. So this is cluster computing, and this was the computing that was used earlier. Okay, so now I'll introduce you to how do you build an actual supercomputer. Okay, so what we know now is that clustering is the way to build a supercomputer. That is acknowledged, right? So now let's see what else can we do to make it actually usable. Okay, so you have compute nodes. Param UR2 uses 288. You can build using 16, 32, whatever your budget permits. Take this many number of nodes and build take those compute nodes. Then you need to connect them. They need to talk to each other. So the network becomes very crucial. Has anybody heard of any network that connects computers? Huh? Pardon me? Blockchain. Which is that? InfiniBand is there, which is a high-speed network, or the cheapest one is a Ethernet or gigabit Ethernet. Okay, so you have a network like this. So the ones that connects computers in your lab, we call it as a local area network. But here we need what is called as a system area network. Okay, which connects the systems. Okay, so it's called as a SAN. So like ParamNet is one that CDAC builds. Similarly, InfiniBand, HDR, FDR, various rates, 100 gigabits per second, 200 gigabytes per second, you get those kind of networks. So this is called as a primary interconnect, which binds all the nodes together. So one compute node wishes to share some data with the other, it will go through this switching fabric. So that is this you can say is the engine of your supercomputer, which does all that is required to run your program. So now, if so many compute nodes are running a program, as was told in the morning, the actual data resides on the hard disk. Your data and code resides on the hard disk. That is a non-volatile memory. If it comes in the RAM or a cache, when you turn off the system, it is going to be lost. So the origin of your program, data and code is in parallel file. So this is a different kind of file system, which is called as a parallel file system. So how is it different from a normal file system is, it allows multiple programs to access parts of a file. Otherwise, if you open a file, it gets locked. Another program cannot open it. But here you have a special file system. I'll give some details about it later, which allows multiple codes, multiple programs to access parts of the file. Now the programmer has to decide how he is going to do it. So that is a parallel file system. Again, see, it's on the same switching fabric, which means the network which is used to exchange information between them also can reach the file system. Now, in the morning you heard about cache, which sits between your main memory and the CPU to speed up the operation. Very similar concept exists here, that this is a parallel file system built using magnetic storage, and as you know, it's a rotating magnetic medium, so the access times are in milliseconds. Now, have you heard about SSDs, right? So they are like flash memories, like your thumb drive. Their access times are much, much faster. So what you do is you put some nodes here which sit between the compute nodes and the parallel file system. The concept is same as cache. Frequently used information is kept here, so that you cannot go. Another attribute, this is big, this is going to be small, because this is costly and takes space. So this is small, fast, maintains a copy of data which belongs to the parallel file. So far so good. Similarly, you have what is called as accelerated compute nodes, which complement the compute nodes. So what are these? All of you heard about GPUs, graphics processing units, okay? They typically work on SIMD principle. So there are some workloads typically that uses graphics, audio, or many such data which are streaming in nature. They can run faster if you have some accelerator. So now accelerators of various types, I may not have time to go through it. One is called as FPGA based accelerator. CUDA is the simplest one that one can put in your computer. So these accelerated nodes, the compute nodes and accelerated nodes together work towards giving a given performance for a parallelized code. So you can say that accelerated compute nodes are extensions of compute nodes. These are CPU only nodes. These are CPU plus GPU or some accelerator built into this. Okay. So now this becomes our basic system using which one can put code and data here, use the compute nodes and the accelerated compute nodes to run your code. But this is not enough for administrating the system. So you have something called as tape library with what is called as hierarchical storage management. All of you know why it is required. You can take backups there, or if you bring data on a tape, it can be loaded here and the data can be taken onto the hard disk. So it's like a backup mechanism. Then other thing here is what is called as login nodes. Very important, because you cannot directly reach the compute nodes. What you have to do is, as a user, you have to log in into these nodes, and from there you will fire a job, and the job will get into the queue. How this is done, Sandeep will explain you day after tomorrow. But like, you cannot directly reach the compute nodes, they are at the back end, but a user has to get into this. Okay. So that is how what the user will do. User will log in into this node, he will present his credentials, and then he will fire a job on this. Now assume there are 300 nodes here, each one will boot up when you start the system. Now to make sure that all of them have the correct image of the OS, that image of the OS is stored here. So these are called as boot servers. So what do boot servers do? They allow the compute nodes to boot. So suppose you want to change the version of the OS. It will be hell of the job if each of these nodes has to be connected a keyboard monitor which is not there and then load the OS. Instead of that, you set it up here. If you notice here, there is another network, 1 gigabit network. What is it used for? It is used only for system administration, a different network. So through this, you only say that you should boot the image, name of the file is so and so, the IP address of the boot server is so and so. When the system boots up, it takes the image from here. So what does the system administrator has to do? He has to just keep one image here, which will be taken by all the compute nodes, and it can be configured. He can say that 10 nodes should have this version, next 10 nodes should have another version. All that is possible through this management node. The management nodes can also capture the individual consoles for debugging, etc. So this is purely for administering the network. Okay. Then how do you land on these login nodes? You will land on the login nodes through a gateway. Let's say entire campus of IIT Kanpur has got its local area network, and there is one computer center where a computer system like this is here. So users are here. Like yesterday, you tried to access CDAC network through what is called as Pravesh. So that was a virtual client. I mean, it's a VPN that you are forming. If you are on the network in the campus, the trust is known that you are a student at IIT Kanpur. You are authorized to access the network. The very fact that you are part of the network gives you the credential that you are authorized. So in that case, you have a networking gateway through which you can enter. From here, you will log in get to the login node. From login node, you will fire the job and it will be run on this. So I hope the architecture of what are the various components in a typical HPC system is clear. Okay. So this has to be supplemented by a stack. Okay, so I will briefly tell without going into much details what it is. So at the base is the operator. So the nodes are here. These are the nodes. On top of the node, each node there will be an operating system. So this is a lightweight operating system. Red Hat, CentOS, SUSE, even Fedora you can use, but it's lightweight. It doesn't have print services. It will not have file services because you don't need them. You only want it to be very small in size so that most of the time is devoted to running your code, and OS will only give you some basic features of starting a process, spawning a process, etc. So that's a lightweight OS. Then there is a middleware. This middleware consists of cluster monitoring because it has to be inherent, whether a node is on or not, whether what it is doing, is it free, all that is managed by this. So there are some known open source tools, or some CDAC has also developed. Then these cluster monitoring tools work with provisioning. So what is provisioning? Allotting a node to a program that the user wants to run. Suppose you log into the nodes and say this is my program, it needs 16 nodes. Who will do that? The provisioning, because it knows which are allotted, which are not allotted. From the free ones, they will be allotted. Process your job ends, they will come back to the pool. So provisioning tools know that how many of the nodes are currently available for starting a job. Then the file system. So this is the parallel file system. So you have NFS. NFS you all know, it is used for sharing data. So like you have a pool of data at one location, through NFS you can share it. But you have some things called as general purpose file system or Luster. These are parallel file systems. So remember we had a parallel, I had shown you a parallel file system here. So this file system that runs here is actually either a Luster or a GPFS or any other such file system. Okay. So that allows access to multiple parts of a file at the same time. And you have the job scheduling. So there are many of them. Some of them like RTR PBS Pro, it's a paid version. Moab or Torque, MOI, they are open source. So the program that is run is through a configuration file which is understood by the resource management, which allocates resources, which allocates nodes and schedules your job. Okay. So this forms the middleware which allows the user to make use of the hardware that is underlying. Then you have the programming tools. In simple, let's say on a Linux system, you write a source code in C, compile it using GDB or Intel compiler and run it. So you just need a loader linker and job is done. But here you have things like, first of all, you need development tools using which you write your code. So you have a compiler like GNU compiler, or there are paid compilers like PGI, or with Intel hardware optimized compilers are available called as Intel Studio XC, or there are third party Alina, which actually Studio contains parallel debugger as well as the compiler. So Alina DDT is actually a parallel debugger. In a normal case, you will need a simpler debugger, or most of the times we solve logical problems by using printfs in our code to see how the code is running, but that may not be possible here. So you need some tools, and they also do as it will told to you. given a code, they also tell you where are the hotspots, means which part of your code is taking most of the time, so that you can target parallelization to that. All that will be told to you later, but these tools, they allow you to do that. And you need, if you are running a parallel code, you need parallel libraries. So this also will be told to you how to use these libraries, like there is a CUDA library, there is a LAPACK library, this all will be told to you, because you can use it in a parallel fashion. And finally, you have something called as performance monitoring tool that runs in parallel with your code and tells you how your code is running. So some details about that will be told to you. So what is the take home message? Take home message is we move from a single processor system with a simple thing like a compiler and a debugger to a complex parallel system which is appropriately supported by a host of middleware and the programming tools that allow you to parallelize your code, run it efficiently. So more about it will be told in the next sessions how that is actually done. But these two slides give you an overview of how the hardware is and what is the environment which a user has to use to make use of the parallel computing system. All right. I hope you got a general idea about it. Yes.
Can I simply deploy that executable on this HPC system without changing anything in the source code?
No, but then it will be run like a serial code. It will make use of only one CPU.
We have to change the source
Yes,
code.
yes,
So
yes.
we have to write our code specifically to according
Yes,
to
yes. And there are various ways of doing that, which I shall give a brief idea about that in the.
And so we are including more and more cluster nodes in the hope of that we will improve performance, we will reduce runtime. So is it possible that it could have negative effects also, like more communication overhead, so eventually performance could reduce because of communication overhead?
So that you will have to that becomes a part of how you design your algorithm. Okay. So it can be counterproductive, yes, if not done correctly. That is very much possible. So there are some standard ways of doing it. If you follow them, then your actually time is going to reduce. But if you don't follow them, or you see, like to give an example, morning he explained about cache and he talked about locality. He said that code which is close by or data which is close by is frequently used. That is how the normal way is. But if you write your program in such a way that you use data from different portions, then you will defeat the purpose of cache, and that will be counterproductive. So a cache miss, if it happens too frequently, then the miss penalty is much higher. So you are better off not having cache. So it's something like that you are saying. So theoretically it is possible to beat what it is optimized for, and then show that it is slower. Okay, it's much possible. Yeah, we'll come to you.
So there must be bound on how fast we can, how much fast we can make it, right? Like it's not like we keep on adding parallel nodes.
Correct. So there is a theoretical, there is also, I am not touching on it, but there is an Amdahl's law, okay, which tells in a given code what part can be parallelized and what part is non-parallelized. So it gives even if 90% of your code is parallelizable, still you will not see like x times, suppose you have 10 systems, it will not be 10x, but it may be something like only 6x or 8x. So there is an Amdahl's law which tells you that. Yeah.
So we give programs to the nodes. Does each node have the management for parallelizing it to the whole set of nodes, or when we log in SSH into the node, we are actually SSHing into the management node?
You are SSHing into the login nodes, not management node. Management nodes are used by system administrator. There was a login node which I showed you. So these are the login nodes. You will land on this SSH here, and there is a way of submitting job which we will told to you day after tomorrow. How do you submit a job? Because there is a configuration file, and there is an executable, and there is a data. So this will be told to you. Yeah, no, so management of what? Yes. See, so there is this guy here, provisioning, which will say which nodes are allotted for that job, and that will be managed by this the framework, the parallel framework.
Provisioning middleware is only it's not given to all.
No, that is transparent to the user. that something exists, the user is not directly talking to the provisioning. It's a method by which it will be told to you. Like if it's MPI, there is an MPI run environment which does that. So it will be clear to you once it's shown, told to you day after tomorrow.
Suppose we have a system, high performance computing, and we use the speed up of K, but at the same time we saw that there is a network into which users can SSH into, and say there are K users logging in and submitting their jobs. So the speed up will effectively goes down to 1 now. So isn't the entire purpose of HPC defeated in there?
Not really. See, if there are at a time, a node will not be allotted to more than one user. Okay. Suppose a cluster contains some n number of nodes, and there are some set of users. The total requirement of the users, number of nodes of the total, if you sum them up, it cannot be more than what number of nodes you have. So at any given time, a node is allotted to one user till he relinquishes that node. Okay. So it's not that a same node gets used up by more than one job. No. Then you will take time in switching them. So that's what we don't want. So a job may wait for a long time to get the requisite number of nodes. So only when the job gets the requisite number of nodes, it is submitted for, it comes up for execution. Yeah.
Process is acting a particular current that will be locked.
Yeah.
So as you said that it allows multiple programs to access the same part of file.
No, one program, one user's program. See, what you are doing is you are breaking a program into multiple sets, each running on one processing unit. And each processing unit wants its data. But the whole data all the data is in one file. So one process needs some part of data. So you can log those files for reading or write only. So that parallel file system also maintains metadata as to what process is using what part of the file system in what mode. And in the simplest case, assume that the entire file is read only. Then any process can read any part of the file, right? But suppose you declare some portion as write, that will be allotted to only one process, so that another process cannot write it at the same time. So that is done by the parallel file system. Yes, that is taken. See, first of all, your algorithm has to be such that you are clear that which processes or which part of your program is reading, which part of the program is writing. That is the precaution that as a programmer you take. If you fail to do that, there will be some locking mechanism that the parallel file system will provide. So you may get an error saying that you are unable to read that or unable to write that, right? So then you will have to debug your program and make sure that your algorithm is correct, which is supplemented by the file system, which gives you certain features.
So does each node have its operating system?
Yes, lie to it. Each node has it. So we are talking about cluster. Remember that a cluster, what I showed you here, that each of these compute node has its own operating system.
We don't have a single operating system for all entities.
No, so one situation is that in this boot server, you say that all 100 nodes will have the same image. That is one option. So all of them will have the same image. And in rare case, if you want, you can also have different images, as I said. If that should that, like let's say some program that you have written needs previous version of OS as a special case. That is also possible. In normal case, all of them will have the same OS.
So it's between like 10 computers.
Exactly. Yes.
One computer having 5 cores.
So right, that is, but under the middleware, what is done is this middleware creates a single system image, a sort of pseudo single system image, but they are autonomous in nature. This is the framework that binds all of them together. So theoretically, suppose there are 1,000 nodes, a single program can run all 1,000 nodes, wherein the user has broken it down in such a way that there are 1,000 different portions of the programs, each running on each node. That is possible. So it allows that. But in real case, what happens is you will need 16 nodes, she will need 32 nodes. So the job scheduler then comes into picture. There are some production systems like weather forecasting, There was an Earth simulator, you might have heard about it in Japan. 10 years ago they built it. It was dedicated for that purpose. So there was nothing else that would run on it, but the entire system was used only for a single purpose. So there are some production systems like that. You are not able to assimilate. Okay? So if majority feels, not one person cannot derail the whole class. But if majority feels that, okay, this is too much or it's not interesting, I will stop. All right? So do let me know. We can have, it's flexible, we have 6 days. I can continue after break. Okay? But I think till 1:15 we should be able, 15 minutes because we started late. Okay? Done? No, I haven't, have I completed your answering your question? Yeah, okay.
Cores in one node we want to have? Like what is beneficial?
Okay, see when you are building cluster, at that time, see these are, remember these are commodity off the shelf we are talking about. We are not designing particularly for this, okay. So typically we will take what is the best available in the market. So today, for a given cost, so typically today, each of these box, typically 2 socket is what is gives you the good price performance. And Intel decides how many cores go into one socket. I think today it is 20 cores. Sandeep, is it the latest one, 20 cores in one CPU? Or is it 18 or 16? Higher version. So again, what happens is those higher, the top of the line will be very costly. So, and your program can adapt to it. Then again, there is another metric, per core, how much main memory are you putting? Okay, so the board should support that. So it has to be a balanced system. So you cannot, there are few parameters like cost. There are typical things like, as I said, 2 socket gives you the sweet spot. Then as many number of cores you have, you should have, because each, remember now each core is running, each core is like one node now, because it has got, it is sharing a, so there is, as will be told to you later, there is something called as symmetric multiprocessing. So all the, if we say 20 plus 20, 40 of them are sharing the same memory. So they will be operating on their portion of the data. So with 40 cores, you cannot be having just 64 GB of memory. You may need 512 GB of memory. So this is some price. Then if the number of nodes become large, your network has to be supporting. So it's a balanced thing that one has to look at, and the accelerator also. Then comes the power. How much power will it consume? So that design has to be balanced. So I may not be able to give an answer in 60 seconds. Okay? But these are the parameters that decide. So this is the last question. Okay, I don't want. I am not discouraging questions, but we have a time limit. We can take later. Okay?
So functionally, how are the accelerated compute boards different?
Correct. So what happens is, typically, I said accelerated compute nodes have accelerators. Theoretically, you can populate all of these with accelerators. Okay, but that will increase the cost. So typically what is done is, some nodes, so these basic nodes, there is no difference between the 2 nodes. They are exactly same, but some of them come with accelerator. Like maybe later I can explain you how the accelerators work, but at this point just remember that you can offload some task to them. Okay, so the accelerators work in conjunction with the base CPU. So you have to, again you have to intelligently divide the task between the base CPU, so that Bharat from NVIDIA, who is coming next week, will tell you how CUDA programs are written. What are their limitations? Like the data is in the main memory, but it has to be given, the relevant data has to be given to the CUDA memory. So again, that is a part of the algorithm, how that has to be done. Okay. So, but it is not like saying that the main computers are having Ambassador engine and the accelerator computers have got Ferrari engine. It's not like that. That same thing will, if you put it there, will run faster. It is not like that. We call it accelerated nodes because they have some computing elements which are tuned for certain workload, certain types of workload. Like CUDA is good at SIMD. CUDA has got good affinity or has affinity towards SIMD kind of workload. So that will be told to you when you study. So every problem does not have a single solution that you do this and everything will go fast. It is not like that. You have to see whether, beginning with whether a code can be parallelized. You have to start with there. So that will be told to you in the. Okay, so I will take rest of the questions in the break, because I have few slides to cover and I don't want you to lose that. Okay, so this is the stack. So now, why do you go for parallel computing? You have a single CPU systems, SISD. Your every job that you can think of in this world will definitely run on it. There is no doubt about it. It will run. The question is, how much time will it take? Does it have enough memory to support that load? But hierarchical memory, you can build, data will come. If not in main memory, it will come from hard disk. If not in hard disk, it can come from network storage. If not in network storage, NFS, it will come from backup. But your program will run. It may take a year, but it will run. But you build better systems using how? So in single CPU system itself, so first thing when you want to parallelize, you have to first see what best I can achieve out of a single node. Then you go for multiple nodes. Okay, so what is that industry has done to improve a single node performance? 8085 was 8-bit, 8086 was 16-bit, 386 was 32-bit, Pentium latest versions are 64-bit. So what we are doing? Increasing ALU width. In the morning he told you, the size of the register, increase size of the register, increase size of the ALU, more bits in parallel, I mean your accuracy increases, or what you would do in parts, you can do it in one shot. Clock frequency, you can increase. 8085 was 3.77, 8086 was 4.77 megahertz. You got processors that went up to 4 gigahertz, but now you have come down because of some reasons like power dissipated is proportional to square of frequency. So if you double the frequency, your power consumption becomes 4 times, and extracting that out is not easy. So, but there is a limit. Pipelining, it was explained to you in the morning, I will touch upon it later. Improved compilers, like which convert the higher level language into efficient machine level language. But there is a limit how you can reach in each one of them. So you have to go for parallel computing. Okay, so what do? First, as I said, they, in broad sense, they overcome the limitations that single CPU systems they offer. So why is that so? The sequential systems are slow. I already told you, calculation may take days, weeks, years, because that depends on the data and the algorithm that you're using. When you have more CPUs, I told you in the morning, parallelizing, so they can do the software. There are one is slow, second is they are small, meaning every, like a 32-bit processor with 32-bit address can only physically support 4 GB of memory. It cannot go beyond that, which means the data set may not fit in the memory. You have a single processor, so that same problem, not in main memory, so go to the hard disk, all that problem will come. But if you have more CPU, each one can have 4 GB, 100 CPUs, 400 GB, so more data. So what are we getting? We are doing it faster because we are dividing the task. We are also able to solve bigger problems. That's why these are the two basic motivations why we go for parallelizing your code. Okay. So instruction level parallelizing, that is single CPU. In this you can do pipelining. You can do what is called as superscalar. I will explain each one of them. This was explained to you in the pipeline processor. Processor which is non-pipelined does fetch, decode, execute, write. Then fetch, decode, execute, write. So 4 cycles per instruction. In the morning he said 5. There was one more in that, but this is memory access, something like that. So now if this was the case in a non-pipeline processor, in pipeline processor what you do is that you have now, see 2 was here, now 2 is fetched when the second one is, first one is decoded, right? These are the clocks. So we have cycles here and the instructions that are getting. So if you notice here, what we have done, we have compressed it, because in this, when decode instruction was getting decoded, fetch unit, execute unit, write unit were free. So what we did was, why, if this unit is free, why can't we fetch instruction 2 here? In the third cycle, when it goes for, the first instruction goes for execution, red one is instruction 1. I hope you realize it is, instruction 1 is red. This instruction is yellow, light yellow like this. So we are overlapping in the same clock cycle, we are doing multiple things. So what is the result? Each instruction is still taking 4 clocks to execute, but by compacting, after a delay of 3 clock cycles here, every clock we are getting 1 instruction. That's what he mentioned in the morning. 1 cycles per instruction is become 1, though each instruction is taking 4 cycles. But number of effective cycles required are 1, because one after another each cycle is finishing its execution. So this delay, now that bubble in the pipeline now will come if there is a branch instruction, but this is how we are increasing the, now today as you said, every processor is pipeline, because now it's not 4 but 10, 12, whatever the case may be. Okay? So instruction parallelism, number of parallel stages. Superscalar, what we do is, in a scalar unit, you do not have these execution unit. You have a single stream which goes through one execution unit. In superscalar, you increase the number of execution unit. Everything is same. Register is same. Unit, all these units are same. So what you see here, instructions are sequential. Like somebody mentioned, my program is sequential. If I run it on a parallel code, what will happen? It will run sequentially. But if you run the serial code on a superscalar processor, where the issuing is done dynamically, Pentium does that. Which means, in Pentium there are 2 execution units. So in the simplest form, assume that all odd instructions are executed by one unit, all even instructions are executed by other unit. Your speed up will be 2x, but that will not happen because there are control and data dependencies. But in simple form, a superscalar processor has a capacity to speed up a serial code. Theoretically, yes, it can do it. Okay? So the answer to that question is, if you have 4-way superscalar, your code can run in 1/4 the time theoretically. You can prove that, but provided your code has no control or data dependency, which is may not be a practical program, but it can only be a theoretical program. So superscalar, no change in the code. Now remember, this we are talking about a single CPU. We have still not gone into parallelism. Okay? So sequential instruction, but dynamically they are multiple issued. Multi-core. Now see the difference between the two. In this case, in superscalar, we are only duplicating the execution unit which are inside, okay, the ALUs. Whereas here, the entire CPU core is duplicated. Means you have 2 instances of Pentium inside the one chip. Why this is possible? Because of more number of transistors you can pack. You are getting billions of transistors now available. So now the architecture is like this, that you have multiple cores, it has got linked L1 cache. So this is a private cache. This cache is linked to this core, this cache is linked to this core, whereas you have a common L2 cache. In this case, in this example, in a latest processor that you have private L1, L2 caches and linked L3 cache. So this is one example which tells that data required local to this core resides here, data to be shared resides here, and the main memory is here. The dynamic RAM that he showed you is here. In the morning he showed you the DRAM controller inside the CPU, which is here, right? I hope you are getting what we are saying. Again I will repeat, superscalar like a Pentium old processor, only the execution units are duplicated. Here, when you have an i5, 4-core i5, you will have 4 such independent cores. So OS could be running on this, application program could be running on this independently. Plus hyper-threading, other things which I will not get into those details, but you are getting more cores. Now core, understand the difference between core is inside a CPU. So one socket physically that you see can have 4 actual CPUs or 2 actual CPUs. Okay? Like you mentioned, for server class it can go up to 20. So you will have 20 such CPU cores, each having L1 and L2 private caches and a common L3 cache in the newer processors. Okay. Now comes this important thing called as advanced vector instructions. So these are instructions inside the CPU. Okay. Intel processor can have it. CUDA is what introduced this, but now Intel also has it. So what it does is it takes advantage of single instruction multiple data. So they were introduced by Intel and AMD in the x86 processors. So their latest processor, I cannot remember which processor onwards, but they have this. So what is it? It is called as AVX512. So normally one instruction operates on one data, but what they do is this instruction can take 512 bits at a time and operate some, let's say, XORing two numbers or any operation that you can think of. But typically a normal processor, an old processor would, without AVX extension, would operate on one data that is in the register. But now there are AVX register in which what you can do is, as mentioned here, there are, if you are doing double precision arithmetic, 32 data can be operated simultaneously by single instruction. See, instruction is same, whatever it is, but it can operate it on a set of 32 double precision. If the precision is reduced to half, which means the accuracy becomes half, then you can take it for 64. Like AI and other workloads, you don't need double precisions. You may need even single precision, so 64. So what is this? Otherwise, if you go to the other end, instead of 32, it can become 8. So what we are essentially saying is, you have 512 bits, you can either divide it into 32 of double precision or 64 of single precision. That you tell how that instruction should work. So this is, why do we need this, or what is the advantage of this? It accelerates performance for workloads such as scientific simulation, artificial intelligence, deep learning, typically image and video processing, where streaming data, constantly a set of data is coming. Earlier you would take one data at a time and operate. Now you are picking up 4 chunks, 8 chunks of them. So your time is reduced, because your aim is what? Your aim is single instruction, multiple data. Okay, that is the next thing that is being done. Okay, so now this is all about the architecture, all the hardware aspects. Now we will talk about the parallelizing approach that we have to take. Okay, so there is two types of parallelism. One is called as implicit, another is called as explicit. As the name suggests, implicit, it is done by the compiler. So now OpenMP, that will be told to you, the first thing that he will tell you, OpenMP, that follows this, that you tell compiler, this is my do loop, please parallelize it. You don't have to do anything, the compiler will do. It is very simple, right? So automatically it will detect, there is a for loop, it will parallelize it. Then it will assign the task, control, synchronize, everything is done by implicitly done by the compiler. User doesn't have to do it. So what is the advantage? Advantage is that the user doesn't have to worry too much about how to parallelize the code. It is very general, flexible, easy to do, but you cannot have efficient solution. Why? Because the compiler is doing it. What is compiler? Compiler is a program. It is written by another programmer. So it will have limitation. No program can do things better than a human mind can do. We know all that. So we call it as artificial intelligence. Artificial intelligence cannot be same as natural intelligence. It may tend towards natural intelligence, better and better systems, but human mind can never be beaten. The best human mind can never be beaten by any program like a compiler, that we know. So what is the other option? You do explicit. As the name suggests, it's explicit. So what is the responsibility of the programmer? He has to decide what are the tasks for parallelism. You don't leave it to the compiler. You decide, okay, this is what I can do. Then assign the task to the processor. Whatever was compiler doing in the previous case, you are doing everything. That's why we call it explicit. So why do we use this? It is for experienced programmers. The compute communication overlap, race conditions, how you can take advantage of the architecture, all that the programmer can do. As a result, the best possible performance for a given problem can be achieved. The previous model cannot do it. But what is the disadvantage? Programmers are responsible for every details, means you have to be an experienced programmer. They have deep knowledge, So one is meant for those who are starting. Once you gain that knowledge, you get that expertise, you can switch over to explicit parallelism. So both of these exist, it's up to you which one to use. So there are two models that exist. One is called a shared variable model, other is called as a message passing model. So what are they? In shared memory model, this is like one motherboard having multiple CPUs and they are all sharing the same memory. This architecture is called as symmetric multiprocessing architecture. So as a result, what happens is, this is easy to do because one CPU writes in the memory, all other CPUs can see that. You don't have to explicitly communicate. But building such bigger systems are very costly because the hardware becomes costly. So this is one way. So SMP, one node that you have in your compute as a compute node will have this model, that all the processors will share the same memory. What is the other way? So what is the good thing about it? You have multiple threads, they share the memory resources. You don't have to explicitly, so all these things it will be evident to you as you study how OpenMP works. So communication is implicit, means one processor writes the data, all others can see it because they are sharing the memory. Okay. Now these are the advantages. The data sharing between thread is fast, one process writes, others can see it. There is, all of them share a single address space, so you have to divide it and allocate to different processors. But there is this disadvantage is that you cannot build bigger systems, but programmer has to specify locks. I will explain that in the slides to come. Whereas message passing model, now this is one node, this is another node, and this is your InfiniBand network. So there has to be a process called send here, and there has to be a process called receive here. Only then they can talk to each other. So here you have asynchronous parallelism, means you have to explicitly send the data. The interaction has to be explicit. The address spaces are separate. In the previous case, as you saw, there was a single memory which was shared. That is not the case. This one has got its own memory. This processor has its own memory. This processor has its own memory. So you have to send that data. So data transfer requires cooperative operation. So you have each process has local variables and you have to communicate as shown in that model. Okay. So this is message passing is general model and it can work. MPI, as will be explained to you tomorrow, follows this and things will be more clear to you. The good thing about it is scalability. In the previous case, scalability was not available. So now I will quickly tell you how overall you can parallelize your code. So what are the paradigms for that? So the ideal situation is you divide the work into as many number of processors that you have. Suppose you have 16 processors, you divide the work into 16 processors. And each processor is unique. When you say unique, it is not dependent on others. So it's like there are 10 children in the class, teacher gives each one of them own task that child is doing, not communicating with each other, no time spent in communication. So this is good, and the communication, that makes it unnecessary, and more important is all the processes do equal work. If one finishes fast, others will be waiting, or if one takes long time, n-1 have finished, but nth processor is still doing it. Hence, unique work and equal work. If that is the case, that is the ideal situation, but that will not happen in reality. You will find that there has to be some kind of synchronism required for going forward. Okay. So these are the methods by which you do it. I will explain each one of them. So first look at the phase parallel model. So what you see here, C is the compute part. So you start the program, you divide it, these are the processing elements, each one of them is doing its task. Okay. So there are two phases, and one phase is computation phase, which is independent of each other, and there is an interaction phase. That is where they exchange the data. And another good thing about this synchronous interaction is, in case you want to do what is called as checkpointing, meaning suppose you fire this job and it continuously runs and finishes. And suppose if that is the way you have designed it, and if one of the processor fails or hardware fails or network fails, you have to restart again. But here what you can do is you can write intermediate data to save it on the hard disk or something. So if suppose it fails here, you can start from here. That is the advantage of having this kind of computation phase which is independent and an interaction phase. Here data is exchanged, everybody comes to a same level, from there they again start. I hope you are getting this. So you divide the task, independent task, then at one point they exchange information, I am okay, you are okay, this is data I have for you, give me your data, then again go, the data that has been exchanged, work on it. Okay. So there are, again remember that for a given problem, one of the models will be best suited. So you have to choose it at the beginning of your, when you design the algorithm. Divide and conquer. So first process starts, it divides the data or code to among two children. The children find that again it can be further divided. So the child further divides it to the grandchildren, and you have so many number of processes running. At some point when they finish, they return it back to their parent, and the parent then returns to the grandparent. So like this, there are certain algorithms which are best suited, like quick sort if you want to do, then this can be done. Maybe you already did it on a single processor where it was done through threads, but now imagine you have so many different processors, so that you are not time slicing the main single CPU, but you are giving it to multiple processors. So in which case this divide and conquer is another model. Then there is a pipeline model. There are some kind of workloads wherein you have a data stream that is coming in, and you divide it into a certain set of tasks such that output of P becomes a input to Q. Okay, so you process partly, generate intermediate data, that intermediate data goes to the next stream. So the same concept what we had in the pipeline, that all the stages of the pipeline are always full, but this is the output of this goes here, output of this goes here, that gives you the final result. But while Q is operating on second set of data, R is operating on first set of data, P can operate on the third set of data. And like this, the output of previous stage comes as an input to the next stage. So again remember, for a given workload, one of these models would be best suited, so you have to choose that. Then there is a process farm model. This is very easy to understand. There is one master process which divides the task to the children. So there is only one level of children, so all of them get the task and the data. So multiple workers are spawned, each one of gets the workload from the master, and after processing, the result goes back to the master. So in fact, this model also can be done, converted into master, where the interactions are like not amongst them but goes to a master. Okay, so that can be done. So you have to decide which suits you best, whether the network and other things also matter, which one is the best algorithm for a given architecture. Then there is what is called as a domain decomposition. So wherein, I mean, this is typically used for weather forecasting and other types of code. Your data is like three-dimensional. Assume that you have a three-dimensional matrix on which you have to perform some things. So you assign each of these cubes, smaller cubes, to one process, and then sometimes there are some interaction required between the adjacent ones. So that depends upon how the interaction is required. But this is called as a domain decompositions, and there are some boundary value problems that you need to solve. Typically, they can be best done by this domain decomposition. So that was meant to give you an overall idea about what are the paradigms that you can choose. One of these or a combination of them can be chosen which can be suited for a given problem statement. So now these are the desirable attributes that you see in any parallel algorithm. So first, the most significant being concurrency. If there is no concurrency that you can spot in what you are doing, you cannot parallelize. So this is the ability to perform many actions simultaneously, and typically, as I said, if they can be independent, that will be the best thing that can happen. Then scalability, like suppose you have 4 processors available, each processor does 1/4 of the task. So tomorrow suppose you can afford 8 processors, the algorithm should be such that it can take advantage of the 8. So there are some algorithms that hit a plateau after a certain number of processors, that's very well seen. that it goes from 8, 16, 32, 128, but beyond that it remains steady or sometimes it falls down. So that kind of thing is also observed. That depends upon the algorithm that you choose. Data locality. So if the data can be local to a process, it can be partitioned in such a way so that you don't need to access data from another node, then that is the ideal thing, because the latencies will be very minimal. Finally, modularity, that means it should be modular in nature. You should be able to divide the task into modules. Then it becomes easy to schedule it on a different set of nodes. So these are the following, very simplistic way of telling what you can do, but overall this is what the philosophy followed. You distribute data to the different memories of processors, then you to act on that data you distribute the code, then you choose one of those workflow models, and then first you have to see that your algorithm works correctly. The next step is to go for optimization. So wherein you can have, there are known ways of doing it, like compute communication overlap. While you are computing, the communication network should fetch the data for the next state. Otherwise, you compute and wait for data to come in. That's not a good thing to happen. Sometimes the network supports it, sometimes it doesn't, but depending upon how the overall architecture is, you can tune your algorithm to a given architecture. So this will be covered in details by Bharat from NVIDIA, but this is to tell what that accelerator part is. So a typical thing will have something like a 4-core system, and then now this number has gone today, the best possible CUDA cores that you have, they go into thousands of cores you have. So that number will change, but the fact remains that these are like general purpose and these are tuned for certain workloads. So when you find a pattern which this can do faster, this CPU can offload that task to the CUDA, and CUDA can do it efficiently. Okay? More about this will be covered later. I'll just quickly go through where we find HPC being used. So space science, because one of the big data problems, huge amount of data. Now you are building telescopes like square kilometer array and 30-meter telescopes. So the data that comes from there is huge. So HPC is ideal to process it. Earth science, like understanding Earth, geological, everything. And then the most frequently used is atmospheric science. I will give some details about it later. Then life sciences, this also example I will give you. Nuclear science, simulating reactions, etc. Nanoscience, designing new materials. Then crash simulation, this is one of the hot things that they do, because it is very costly to crash a car multiple number of times. But if you can model it and then simulate the crash, then it will tell you the hotspots. Then the mechanical engineers can refurbish those hotspots, then again simulate it, and when you find that everything looks okay, crash an actual car and verify what you got through simulation is actually what you see in the physical thing. So that is the way they do it. Aerodynamics, like aircraft designing, this is like a CFD application, computational fluid dynamics, how you can design the nose of a aircraft or a missile. So that's all is done. Structural analysis, whether the design is safe. If an earthquake occurs, how will it affect the structure? All that can be simulated, and HPC is required for it. And not to forget, today you are seeing good, very realistic movies, because CUDA and other HPC technologies are silently working behind to generate more and more. This involves a lot of heavy mathematical computation to get a smooth transition, to have a smooth surface. Basically, they build a grid, and on that grid they put a surface, and all those things needs a heavy computation. So you have tools for that, but they will not work fast if you don't have HPC. So I'll give two examples. One is in bioinformatics. So we all know that sometime in early 2000, the entire human genome was mapped. So we know exactly what each strand and what each protein in that strand is meant for. So today you can give your sample of saliva and you will get a thumb drive or a hard disk containing your entire genome sequence, and it has become affordable. So that is very useful, because you can understand how your body is and what it is susceptible to, what diseases that child will suffer. And you might know that these days they are preserving stem cells. there's a new fad that you take the stem cells when the child is born and preserve it, so that some of the drugs or some of the things can be derived from that stem cell, and some kind of diseases that the child may face can be easily tackled or easily taken care of if you have the stem cells. So all that is because there is HPC and we have bioinformatics. So this slide tells that the given increasing number of petaflops or teraflops that you have, what else can you do with it? So bioinformatics is one of the fields where any amount of compute power you give, the scientists are able to consume that because they can do simulations and other things at a finer and finer level. Another example is climate and weather and climate forecasting. So in this case, what we do is we basically use two things, fluid mechanics and thermodynamic equation. And these partial differential equations are to be solved in a 3D space. And for a given boundary conditions, you solve them. So what are these governing equations that we have? First one is conservation of momentum, which is applied to winds. So treat everything from the core of the earth to the ionosphere that you have as one 3D space. And then there are winds. There is, when winds move, there is conservation of mass. When humidity goes from one place to other, there is conservation of moisture. Then there is conservation of energy, where you apply the first law of thermodynamics. And finally, we have P1 V1 upon T1 equal to P2 V2 upon T2. So you apply all this, and these are the equations that you get, which you apply to the entire Earth system. So now I think we don't have enough compute power where you can do a coupled model of everything, that is land, sea, atmosphere. That needs huge compute power, but to some extent we are able to do it. So we get data from radars, we get data from weather station, you get images from satellite. Sometimes aircrafts are commissioned to gather data from specific cyclones that are formed. Then there are ships which also collect data. Like you may be aware that this tsunami, when it happened at Tamil Nadu, we got to know it very late. After that, India has put this kind of buoys, weather buoys, much deeper into the sea. So what happens is these buoys, when the cyclone struck Orissa coast, it was known much in advance. 7 days in advance it was known that a formation is happening tens of kilometers in the sea, and they move slow. So we had enough time. So what we can't do is we cannot prevent the destruction because it is packed in the cyclone that it comes. But what we can do definitely is, if you maybe you were not born at that time, but tens of thousands of people used to die in Andhra Pradesh when cyclones you can see that on Wikipedia, when cyclones used to struck them in the 70s and the early 80s. But today, you are able to evacuate them. Last time I think 4 lakh people were evacuated. Only 4 people died. Why? They refused to come. They didn't heed. So they were left there and they died. But we could save 99.9% of, so lives can be saved through this. So that is what is happening, and better weather predictions can be done when you have more compute power, because what happens is if you have less compute power, your grid becomes coarse. If you have more compute power, you can have the data collected at a shorter distance. That gives you a better prediction. Okay, so that's my email address, which you can write. And now I am open to questions. And I hope you got an overall idea about what those HPC systems are, how those are programmed, and more details about how to actually write the codes will come in the next sessions. But the overall idea, I guess, you got about it. So any specific question about the architecture or the overall way the supercomputers are organized, I can help you answer them. Looks like interrupt from stomach is overriding questions. Doesn't matter. Even I am feeling hungry. So I didn't take, I think, only 15 minutes. We overran, right? So that's fine. Yeah. No. One question.
So you said the source code of any high performance requirement that we have is different for each architecture of the supercomputer we have. So it is not the same code that we run on different supercomputers.
No, what I said was you can see algorithm, like if it's a weather prediction, you know that these are the equations. You have to solve them. Okay. So now this can be adapted to a given architecture in a better way. Suppose it's a Cray computer which is good at vector, then you have to adapt it. I mean, see that how you can take advantage of the features that it is offering. Suppose it is like a CUDA, then of course you will not be rewriting the whole code, but you will look at which portions of that code are better, can be better adapted to a given architecture. So to that extent you can give, and some of these big codes are like written 25-30 years ago. They are written in Fortran and they are millions of lines. So I mean, it's a big effort if you want to rewrite the whole code. If you are doing something new which you are under your control, then of course you can adapt it. But that's why that modularity comes in. If you have it defined in a particular way, or what each task does, each portion of that module does, then it becomes easy to adapt one of the modules to a given architecture. Some of them, see, traditionally they were written for a CPU only thing. This CUDA and other things came later. So we have to put in efforts to see which of the portions of that code are can best extract the performance from the given architecture. So it's an evolving process, and some of and for legacy codes which are already running, which are in production, making those changes requires more effort because they are already there. But if you are doing ab initio, like as a part of research science, it's a research student and you are taken a new problem to solve and you have an architecture in front of you, then it becomes easy to adapt it to that because you are doing ab initio.
Sir, one of the slides you mentioned accelerators. CUDA accelerators are hardware accelerators or programming accelerators?
See, this one, right? No, maybe, okay, doesn't matter. Accelerator, see, as the name suggests, it can do certain thing fast. Okay. So now there are various ways of, what happens is that let's say you don't have any accelerator. Then it's a simple code that you have written, wherein the algorithm that you have in mind, you have translated into a sequence of instructions, some of which are operating in parallel, and your code is running fine. So now, what do accelerators do? So in this, the accelerator, I'll take two examples. One is called as a CUDA. So in this case, that the CUDA comes from the fact that actually it was a graphics processing unit which is adapted for HPC workloads. So this is good at SIMD. So if you have some portions of your code which operates on SIMD kind of data, then you can offload that you just take out the code which is running on the CPU and push that data and write a code which runs on CUDA. Okay. So this is one accelerator that you are doing. Another kind of accelerator is called as field programmable gate array. So whatever algorithm you have written in a C language or a Fortran language, you can write it in a language which is called as VHDL, or it's a hardware description language. So it doesn't run on a CPU, but it gets translated into a series of logic gates, and you may get something like 10 times, 20 times, even 100 times speed up, because hardware is doing it, a specific hardware is doing it. So there is the question that you asked, you still have to program, okay, but instead of a program that is running on the main CPU, which it was doing earlier, you are offloading it to a specialized hardware. So programming has to be done in some form, but it is in a form of a different way, a different paradigm. Okay, so by the way, as an extension to that, you can develop a specialized hardware that runs only one code. Okay, so if you are interested, you can see a company called Shaw, SHAW. They make accelerators for bioinformatics, but that hardware cannot run anything else. It can only run that. That is one extreme. That is the fastest way of running a given code. But it doesn't have any scale, any modularity in the sense that it can run any other code. Yeah.
Suppose there is a cluster which is made of 4 compute nodes, and I give a work to all these 4 compute nodes. Now there is a variable which is dependent, like all these computers are going to share this variable X. Now every node will also have cache memory, so they will take the X variable and keep it in the cache. So how the coherence is maintained of the original X variable if you are sharing across the 4 nodes?
Okay, so if you are asking at the hardware level, then there will be one owner and others will be sharing it, and there will be a mechanism by which if any of the other with which is shared updates it, the main one is also updated. There are a mechanism for that which is called as coherency at the hardware level. But how to make use of such a thing, it will be told to you. What is a global variable, what is a local variable, that will be told to you when you are told how to program them. But at the hardware level, there is a mechanism which makes sure that it is copied. But if you are using a distributed computing kind of architecture, then as I told, the one which is making the change has to propagate it to others. So that is what is a part of the one that will be told to you how to do it using OpenMP and how you do programming using MPI. So as I mentioned to you, when you are doing explicit computing like explicit parallelism like in MPI, it is your responsibility to make sure that that thing is propagated to others. But you have SMP kind of thing where only one process updates it, the sharing is implicit in that. So because there is only one shared variable amongst them, so the hardware automatically does for you. So to answer your question, you should know what the underlying model does it, and if the underlying model does it, you don't have to, programmer doesn't have to do it. If the underlying hardware doesn't do it, the programmer has to explicitly do it.
And if we can take other questions offline, let's go about that.
Thank you.